Hello everyone. So in this session we will discuss about how these floating point numbers are going to be added and subtracted. So already we have seen the format for representing the numbers, how this arithmetic operation is going to be carried out, and the example is also given. Just we will trace it after understanding the flow chart. Okay, so as such we have four steps in implementing this algorithm. The first step is to check for zeros. Why we are checking for zeros? We are checking for the operand and we are deciding the result. Now come to the flow chart. Here this is going to be the common flow chart to proceed with for addition and subtraction. Now if it is going to be addition, we are going to add two numbers, namely x and y. Okay, so first we are checking for x is equal to 0. If x is 0, we have to set the result as y. Obviously if one of the operand is 0, so z is nothing but x plus y. So if x is equal to 0, then answer z will be y. So we are setting y to z. So this is going to be the case for this part. Okay, suppose for example if x is not 0, then we check for the next operand y equal to 0. In case if this y is going to be 0, then the answer will be z is equal to x. So we are setting z equal to x and then return. So this is with respect to addition. In case if it is going to be subtraction, so z is equal to x minus y. If this is going to be the case, again we are checking. Okay, if x is equal to 0, obviously the y answer will be given. Okay, for subtraction always we try the subtraction only by implementing 2's complement addition. Now if x is 0, the answer will be y. Okay, so change the sign of y, and then subtraction is always implemented by 2's complement addition. For 2's complement addition we have to change the sign of y and then we have to add. So that is the step here included, and the answer will become y. Okay, suppose if y is equal to 0, the answer will become x. So for both subtraction and addition, we are checking for 0 for one operand. If one operand is 0, then the result will be the another operand. So this is going to complete the first part of the flowchart. So I think from this stage, so this stage to this stage, this completes the first step, that is checking for zeros. Okay, the second step is align the significant. Why is that we are aligning the significant? Now I think we have just you can see the example here, 0.3 into 10 power 2, 0.2 into 10 power 3. So you just compare the exponents of both the numbers x and y. If they are equal, then you can directly proceed adding the significance as such. If they are not equal, what we have to do? We have to make them equal. That means we have to adjust the exponent. How can we adjust the exponent? Take the smaller exponent and increment till it reaches the bigger exponent, or take the bigger exponent and then decrement till it reaches the smaller one. But as per the example given, we are going to take the smaller exponent and the smaller exponent is going to be made equal. So that step has to be done. So if I simply change the exponent, if I simply increment this exponent to 10 power 3, it is now it is going to affect the value of x. So if I increment the exponent accordingly, I have to adjust the significant. Okay, so that step is going to be taken care by the second phase, that is aligning the significant. Now how we will do? Now you come back here. Okay, if both operands are not 0, then we have to do actual addition or subtraction. Now we will just compare the two exponents. Okay, if the exponents are equal, I think on the safer part, if we just assume that if the exponents are equal, if they are equal, then what we have to do? We can simply add the signed significance. It's simply added. Okay, after adding the significance, there is a possibility that the result could be 0. So you check whether the result is 0. If the result is 0, we cannot normalize the number. So what we are trying to do, if the result is 0, simply set z as 0, because you all know the sum of is x plus y is stored in z. So z will be set to 0 and then you return. Okay, if the significant is not 0, then it means that there could be a possibility for overflow also, because we are adding two numbers. When we add two numbers, there is a possibility for overflow. If there is a overflow, you have to take this path. Okay, if there is no overflow, then what you should do? Add or subtract the significant. The third step is add or subtract the significant. So we have add the signed significant, then check for result 0. If it is 0, you set it, because we have to normalize, we have to skip the normalization step, because 0 number cannot be normalized. So directly you take this path and then return. If the significant is not 0, then you check for overflow condition. If it is not an overflow, then the result has to be normalized. So we just go to the step result normalized, that is the fourth phase, normalize the result. After normalizing the result, then you, if there is a requirement that we have to give some precision, rounded to 2 digits or 3 digits, accordingly you will be rounding the result and then return. So this completes a normalization process also, if it is already normalized. If the result is already normalized, we will round it and then we will return the answer. If the result is not normalized, then what we have to do, we have to normalize. So what is the procedure for normalization? So you will be getting some fraction, already you will be having point, and somewhere we will be having some 1 in the result. Okay, we have to bring this one to the left of this decimal digit. So if I bring this one to the left of the decimal digit, then obviously we will be we have to move this one to the left of the decimal digit. For that purpose, what we have to do, we have to shift the significant left. Only if we shift the significant left, okay, the point can come after this one. Okay, so for that you will be shifting the significant. So whenever you are shifting the significant, what happens, already we have discussed. Suppose for example, if you take a number like 100, if you are shifting this to left, what will happen, it will become 10001, something like this. Okay, so obviously the previous value and the new value, it is getting increased by weight of powers of 2, because a number in one position, 2 power 2 power 0, 2 power 1, 2 power 2, it is in 2 power 2 position. When it shift left, it moves on to 2 power 3. That means the weightage is going to be increased, so the value of the significant gets increased. If the value of the significant gets increased, I have to adjust it by decrementing the exponent. So the exponent want to be decremented, only then it will be equal to the old value. So what I am trying to do, I shift the significant left, only then I can bring this one to the leftmost position. So in order to compensate this operation, I decrement the exponent. So whenever you are decrementing the exponent, you all know incrementing can end up in overflow, decrementing can end up in underflow. So if you decrement the exponent can end up in underflow. If the exponent is going to end up in underflow, then you will report error saying that underflow has occurred, then you will return. Okay. Um, so this is what we are going to follow for normalization. Okay, now we have followed this path. So if the significant is not overflowing, we will just move like this. Suppose in case when you are adding the two significants and if there is an overflow, what happens? So we have the number like this. Okay, we have the significance some number like this, and if there is an overflow, there will be some excess bit here. So someone would have come to this position, so the one which has gone outside should be brought inside. So to adjust that, if there is a overflow, you have to shift the significant right. Okay, so you will be shifting the significant right. Again, the same example you can take. If the number is like this, and if you are shifting the significant right, what will happen? This one will come to this position 000. So already a 1 which is there in 2 power 3 now is moved to 2 power 2. That means the value gets reduced. So if the value is reduced in the significant part, then you have to compensate by incrementing the exponent. So whenever you shift in this direction, shift in the right direction, the weightage gets reduced. So that has to be adjusted by incrementing the exponent. So if there is a significant overflow, to bring in the overflow bit into the significant, I shift towards right, and after shifting, it will change the value. To compensate it, I will increment the exponent. Again, whenever we increment the exponent, there is a possibility for overflow or underflow, but here it is for overflow. So I will check whether exponent is overflowing. If it is not overflowing, I can simply continue the procedure for checking the normalization of the result. So if the exponent is overflowing, I cannot do further. So I will just report overflow and then I will return. So this completes the discussion of this path. Okay. Now I think we safely assumed in the beginning the exponents are equal, so we have done like this. Suppose in case if the exponents are not equal, if it is no, that means checking for zeros and then you are aligning the significant. When you will align the significant to make the to make the exponents equal, only if the exponents are equal I can proceed addition. So I have to adjust the exponent. So I told that the exponents are not equal. Then what is the two cases available? The smaller exponent can be incremented or the bigger exponent can be decremented, so that it will be made equal. Now I am just going to select the first choice of incrementing the smaller exponent. So increment the smaller exponent. So whenever you increment the smaller exponent, what will happen? The value is going to be increased. So I have to compensate it. So to compensate it, what should I do? Only if I shift the significant right, the value will be adjusted. So I will be shifting the significant right. Okay. When you shift the significant right, okay, the significant could be some number like this. Okay, 0 0 1 0 1, something like this. So whenever you're shifting the significant, there is a possibility that this all these ones can go out. So there is a possibility that the significant can become 0 when you're shifting right. For example, if the significant is like this, and if I'm shifting towards right, this one may be left out and the entire result could be 0. So the significant can end up in 0. if it is going to be resulting in 0, then what happens? One of the operand is going to be 0, because I adjust the exponent, one of the operand itself becomes 0. So you put the answer as the remaining number. So as we done here, here we are getting an operand 0. Why we are getting the operand 0? We are shifting the significant, right? Why we are shifting significant, right? We have incremented the smaller exponent. So incrementing the smaller exponent will increase the value. To compensate, I shift the significant, right? Because I am shifting the significant, right, there is a possibility it may end up in 0. So one important case could be like this. Suppose if you have a number like 0.0001, that's just the 4 digits. Now what happens? I increment the exponent, so to adjust I shift the significant, so the possibility of the significant could become 0. So if the significant itself is going to be 0, obviously the answer will be the leftover operand. So put the next number in the Z and then return. So this completes the discussion of the process of addition and subtraction, how it is going to happen. So it is going to be done in the phased manner. The first phase will check for 0. If x is 0, answer will be y. If y is 0, answer will be z. And if it is going to be a subtraction operation, you always change the sign of the second operand and then do the addition. Okay, so this is going to be the first phase. The second phase is you have to compare the two exponents. If the exponents are equal, simply go to the third phase where we will be adding. And after adding, the significant is 0, we cannot normalize, so we will just simply return the answer as 0 and then come out. Otherwise what you will be doing, if the significant is not 0, then because you have added the significance, there could be two cases. One is it can be 0 or it can be overflow, because we are adding. So first case is 0, so that we have checked it out. The other case is overflow, so I will be checking for overflow. If it is not overflowing, then you go to normalization. If it is overflowing, then I should bring in the excess digit, bring in the digit which has gone out. Okay, so for that purpose I have to shift right. So when shift right, increment the exponent, then exponent overflow. If you increment, always you have to check for overflow condition, report overflow. And this completes this flow, this part of the flow chart. And if the result is already normalized, you round it and then give it as an answer. If the result is not normalized, you have to normalize. What actually we mean by normalizing? We have to catch a one which is in the right extreme. So this one has to be brought to the left side. So I have to shift the significant left. So whenever I shift the significant left, I have to decrement the exponent, and the decrementing will end up in underflow. So I will be checking for underflow and then report underflow, then return. Okay, and this path, if the exponents are equal, we always make an attempt to bring the smaller exponent equal to the bigger exponent. So increment it. As we increment the exponent, the value has to be compensated by shifting the significant right. So when you shift the significant right, it may end up in 0. If it is 0, then obviously the remaining answer, the remaining operand will be the answer. So put the remaining value as an answer and then return. Already this answer, this operand will be in the normalized form. So we are just going to return as such. No need to normalize here. So this completes the discussion of the entire floating point representation. So one important point what I should emphasize here is that, okay, so every time we are trying to compare the exponents. Okay, so if we are trying to compare the exponents, we are taking the smaller exponent. We have a significant. Okay, let me just write it down here. We have the significant, we have the exponent. Okay, so important point to be remembered is, whenever I increment the exponent, it may end up in overflow, so that you have to check it. Whenever I decrement the exponent, it may end up in underflow, so that you have to check it. Okay, so this is one important point. Another point is, whenever I increment the exponent, what happens? The total value weightage is going to be increased. So if it is going to be increased, I have to adjust that in the significant portion. So how to adjust? I have to decrement the value. So when I will get the value, see, if a number is like this, 0100, if I shift left, if I shift left, the magnitude is increased. If I shift right, then the magnitude is decreased. So this point also you have to keep it in mind. So as far as a given binary pattern is concerned, whenever we shift the number towards left direction, the value is going to be incremented. Whenever we shift towards right, the value is going to be decremented. Now here, whenever I increment the exponent, that means I am increasing the total value. That has to be compensated by reducing the weightage of the significant. How can we reduce? By shifting right. So whenever I increment the exponent, I have to shift right. Similarly, whenever I decrement the exponent, the value is going to be reduced. So that has to be compensated by incrementing the significant. So the significant can be incremented only if you do the shift left operation. So what is the key point to be remembered? Whenever I shift left the significant, decrement the exponent. Whenever I shift right the significant, increment it. Or if I increment the exponent, adjust it by shifting right. If I decrement the exponent, adjust it by shift left. So this is going to be the like a kind of a thumb rule. So if you just look into the flow chart, when we shift left, okay, we have to decrement. So shift left, decrement. And now here, if we increment the smaller exponent, increment means shift right. So we are doing the shift right. So if this point is kept in mind, I think it will be equal. It will be easy.